This video is my attempt to explain for the benefit of my family and friends what my PhD dissertation in philosophy of science is all about. I've been working on this thing for 5.5 years. It took me 8 years to do the whole PhD. And that whole time, I've never been completely satisfied with the answers that I've given my loving and supportive family and friends when they ask me, so what is it that you're working on? So this video is my best shot at it. Hopefully I can hit some of the highlights, some of the interesting bits, and communicate at least some of what I've been working on this whole time. So here's my dissertation. It's called Medium Strength Modality in Science. It's about 180 pages. It's got 7 chapters, 70,000 words, and I think the best way of explaining what it's about is actually to go chronologically, to sort of start from where I started, what questions I was trying to find answers to, because the questions led me to some quite unexpected places in philosophy. This was not the thesis that I expected to write going into grad school. So going chronologically will kind of hopefully put a frame around it and show you why I was pursuing the questions that I was. So let's actually start way back in the late 1990s when I was in high school. One sunny summer day, a friend called me up and was very upset. She was really upset because her long-term committed boyfriend had told her that he thought that love is just a chemical reaction. He said to her, love is just a chemical reaction, sort of just a biological program acting itself out in his brain. And I hope you can see why she might be upset by that. He was writing himself out of the causal story of his own love, right? He was, in some sense, dehumanizing himself by saying that he's just sort of subject to this chemical program that's acting out in him. So I don't think I had anything, I don't recall exactly what I said to her at the time. I don't think I had anything particularly helpful or comforting to say, but that kind of stuck with me. So that and a bunch of other questions like that, where it seemed like there was this tension between understanding ourselves as objects viewed through the lens of science and understanding ourselves as whole human people with beliefs and desires and agency in the world and kind of a place in the causal order of things, right? So it can feel sometimes like the more science uncovers, the less humanity is left. That seems like a deep tension to me, and so that kind of issue is what got me interested in philosophy of science in the first place. The philosopher of science Wilfrid Sellars has a really great paper on this called Philosophy and the Scientific Image of Man, and it opens with my absolute favorite definition of philosophy in the world. He says philosophy is, abstractly formulated, is the project of trying to see how things, in the most general sense of the term of things, hang together in the most general sense of hang together. And that's how I think of philosophy. I think the goal of philosophy is to be a specialist in the big picture and to try to figure out how different ways of seeing ourselves and the world fit together. And in this paper, Sellars specifically talks about this thing that I was worried about, which is the two images of ourselves that we have. The scientific image, where we're a bunch of atoms that make up molecules, that make up cells, that make up organs, that make up organisms, and love is just a chemical reaction. That's the scientific view, or apparently the scientific view. And the manifest image of humanity, which is the image that we have of ourselves from the first person perspective, where we have beliefs and desires and goals, and we do things, we're free to do some things, we can change the way that things go, right? So the whole human experience is what constitutes the manifest image. So Sellars' question is, how do we get these two images of ourselves, one through the microscope and one through our own eyeballs, to fit together? And can they fit together? People have been debating this for quite some time, and some people have gone to one side or the other. They say, look, we have to give up, if you're going to be serious about the scientific image of humanity, you have to give up the manifest image. You have to give up the first person perspective. Other people have said, look, if we're going to take the first person perspective seriously, you kind of have to give up on the scientific project. And neither of those seemed really satisfactory to me. So it always seems to me that there should be some way of having both of these images. You don't have to reduce the world just to one way of seeing. All we have to do is show how they might be compatible. And so that was my sort of motivation for this project, to show that, yes, in fact, love is instantiated by a chemical reaction. Like, if you took away all of my atoms, there wouldn't be any stuff left. My atoms are all there are to me. But at the same time, it's wrong to say that I'm just a bunch of atoms, right? That misses something really important about me, which is, my overall wholeness, my organization as a whole organism, as a person. So my basic motivation going into this project was to try to reduce the apparent tension between these two ways of understanding ourselves. Furthermore, even within the scientific image of humanity or of the world, it struck me that reductionism wasn't doing all that well. So even within the scientific image, reductionism was kind of going out of fashion. For most of the history of science, reductionism was a really great strategy. Like, it was the only strategy. You took a system apart into its constituent parts, studied the parts, and once you understood the parts, you could transfer that understanding to the system as a whole. It was a great strategy. It is a great strategy for tons of systems. Like, reductionism as a methodological strategy is great for tons of stuff. But around the middle of the 20th century, the computer revolution happened, and that radically changed how complex systems we could deal with. So the level of complexity that we could cope with in terms of collecting, processing, and storing information went up wildly, like humongous increase. And so scientists started looking at much more complex systems. And when they started looking at these complex systems, the reductionist strategy didn't look as appealing. It seemed much more fruitful to consider the structure of these systems as organized wholes, rather than to try to reduce them down to their parts. So this is the literature on self-organization or complexity and chaos. So in the late 20th century and early 21st century, philosophers started getting on this train as well, and talking about how even within the scientific image, reductionism doesn't always work. Right? The kind of systems that they had in mind were things like, the iconic one is a flock of birds, where the flock seems to have a kind of intelligence of its own, right? It's got a kind of direction of its own, and no individual bird is leading it, but there's a kind of overall organization and coherence. Similarly, people talked about convection rolls as self-organized. They talked about lasers. That was a big one in the 60s. So a laser is what happens when you excite a bunch of atoms with electricity, and if you do it just right, they start emitting photons. And the atoms, although they could conceivably be out of sync, they kind of push and pull on each other in a way that brings them into synchrony, right? So they start letting off photon bursts in sync, right? And that's what a laser is. It's just a highly synchronized light ray, right? So this is another example of things that look like they're disordered on the level of their parts, but when you get them all together, suddenly this beautiful orderliness emerges. It's an emergent property, they call it. And if you want to see a really nice intuitive version of this, Google synchronizing metronomes. So you can put 32 metronomes on a piece of styrofoam and set them all off. So long as they're at the same frequency, you set them all off at different starting points, and over the course of just a couple of minutes, they will push and pull on each other in such a way that they all become synchronized. It's amazing. It's mesmerizing to watch. So if you want to see this sort of self-organization in action, that's the most vivid, intuitive version of it that I know. So the point is just that there's this rising movement within even the scientific image of humanity that reductionism is not always going to work. So not all wholes are reducible to the sum of their parts. And that was the basic philosophical thesis that I was interested in pursuing. I wanted to show a way of understanding physical systems in non-reductive terms. Okay, so now we've gotten to the point where I can explain what my basic question was, what my motivating question was, and it was this stuff about reductionism and whether we should always be reductionists, whether it always makes sense to pursue a reductionist explanation. The thesis that I wanted to defend is what's called non-reductive physicalism. So can we say both that physicalism is true, and physicalism is the view that the world is just made up of matter and energy, just matter and energy flying around. So there's no extra soul stuff. There's no extra mental stuff or something like that. So can you be a physicalist and at the same time be non-reductivist? So a reductionist says everything is just the sum of its parts. There's nothing in the world that needs to be explained in any other terms than just as a bunch of parts. And there's two kind of versions of that. You can be an ontological reductionist or an epistemic reductionist. So an ontological reductionist says, as a matter of physical fact, if you took away all of my atoms, there'd be nothing left. And I kind of want to accept that. Like, maybe there's a soul. It's a great big universe. I haven't seen it all. But can we assume that there's just matter in motion, but at the same time resist reductionism in some cases, right? There's lots of things about which reductionism is a perfectly good explanatory strategy, but are there some cases in which the best explanation isn't at the level of the parts? For example, things like consciousness, love, and maybe even lasers. So, non-reductive physicalism was the thesis that I was trying to defend. It struck me that this is a thing that should be possible, and there was a bunch of arguments in philosophy trying to show that it's impossible. So there were some famous arguments saying that non-reductive physicalism is incoherent. You can't have both. And that struck me as saying that we kind of have to pick between the scientific and the manifest image. And that struck me as wrong for a bunch of reasons. So that was the idea that got me into grad school. I thought it was pretty good at the time. I thought I would, do my 2 years of coursework and then write this thing up in maybe a couple months, a couple more months to stick in the appropriate references, and I'd be done. I wondered what I would do with the other 2 years of funding that I had left. Of course, it didn't actually work out that way. It turns out this project was much bigger and harder than I thought it was. And the main thing that took me so long was the concepts that I was trying to cash out this explanation in turned out to be very vague. So I started out with not talking in terms of generality, but talking in terms of analytic and holistic explanations. Some of my family might remember me talking in those terms way back when. And I found that those terms, when I tried to really get precise about what I meant by those things, they weren't all that clear. They were kind of mushy concepts at their heart. They just were used to mean a bunch of different things in a bunch of different contexts. So to try to explain what I meant by analytic and holistic, I kind of dug into other concepts like William Whewell talks about ideographic and nomothetic explanations. Those turned out to be not that clear either. I talked about historicity for a long time, so I was really influenced by hanging out with historians, and I found that they had what I described as a holistic method of explanation. They weren't interested in the generalities, they were interested in sort of specific contextual stuff. So I spent 2 years talking about historicity and trying to characterize that precisely. I tried to characterize it in terms of linearity and non-linearity. And that project was mildly successful, but it really still wasn't doing the trick. I still wasn't coming up with a nice, crisp definition of the terms that I was using. So after the historicity and nonlinearity phase, I moved on to generality. So this is the concepts that sort of eventually formed the center of my thesis was generality. Generality and its opposite, contingency. So, but again, I mean, I've tried to dig into these concepts and found that nobody had defined them in a way that was precise enough for the project that I was trying to pursue. Right? So generality had been defined a couple of times in the philosophy literature, but I think it's just such a familiar concept. Like, it's so obvious and transparent what you mean by that nobody had really spent a lot of time on characterizing it. So what I needed to do was define generality. And then once having defined generality, I could use it to explain this position I was trying to defend about non-reductive physicalism. So I said at the beginning of this thing that this was not exactly the thesis that I expected to write. I mean, it would be surprising, I think, if I wrote exactly the thesis that I was expecting to write, but the stuff about generality actually occupies almost all of my thesis. So everything that I've been saying about non-reductive physicalism is actually all in just chapter 6 of 7 chapters in the final product. everything else is dedicated to trying to understand generality and trying to define it precisely, and then deploy that definition in a couple different problems in philosophy to show that it's worthwhile and that kind of stuff. So this is the work that I had the absolute most help with. I co-authored a paper with one of my colleagues at the Institute for History and Philosophy of Science and Technology, Chris Belanger. Chris and I go way back, but we had this really productive collaboration on doing what we called a measure-theoretic definition of generality. So this is so far my one published paper is on this topic. I co-authored it with Chris, and what we did was try to provide a kind of mathematical, formal framework for defining exactly what you mean by generality in a context. And that's really the main bulk of my thesis, is about that, right? And this was all in service of, in my mind at least, trying to explain this thing that I went into grad school thinking. But actually, I think most of the philosophically interesting stuff came out of just really thinking hard about generality and what it means for something to be general. So that's pretty much what I'm going to talk about for the rest of this video, is generality and what we claim you need to have in place in order to say precisely how general something is. So, of course, Chris and I weren't working in a vacuum. There were philosophers talking about generality before us, and one of the most useful distinctions that we drew on was from a philosopher called Jonathan Weisberg, who distinguishes between agenerality and p-generality. So, agenerality is generality ranging over actual things, and p-generality is generality ranging over possible things. So, if I say, generally my students did well on the test, I'm just talking about the actual students in my actual class and how they actually did on the test. There's nothing about sort of the possible worlds going on in the background there. But when a scientist says that they have a general model of something, what they typically mean is that they have a model that would apply across lots of possible configurations of the system, right? They don't just mean that it happens to work today. They mean that even if things were to change, if the background conditions were to be altered, a good general model would still apply. And a general model does things like tell you how to change the world to bring about an outcome that you want, or to predict or to explain novel situations, right? So a good general model in science applies widely across possible states of affairs, not just actual states of affairs. So the kind of generality we're interested in is p-generality. Right, so the paper that Chris and I wrote together was an attempt to give a really nice, precise definition of p-generality. And what we argue is that p-generality means quite different things in different contexts. So in different sciences, what it means for something to be general is quite different and often sort of incomparable between domains. So philosophers have tended to focus mainly on logical possibilities or conceptual possibilities or the broadest domains of like physical possibilities. So what things are licensed by physics. So there's probably some sense in which it's logically possible or physically possible that I might become an Olympic high jumper. Right? So there's no conceptual problem there. It's not that it's incoherent, like I didn't just say a contradiction, which makes it logically possible. But there's definitely a sort of more focused sense of possibility, or like across the domain of biological possibilities, for example, where it's not possible for me to become an Olympic athlete at this point in my life, right? Like I'm a doughy 35-year-old scholar with very little natural talent or training, right? So probably from the set of biological possibilities, there's none in there where I become an Olympic high jumper, right? So what's possible depends intensely on what domain we're talking about. So you have to specify, before you're saying something is possible or something is general within a domain, you have to say which domain you're talking about. And furthermore, you have to say how you're measuring it, right? So how do you assign neighborhoods to your domain of possibility, and how do you carve it up? How do you quantify those neighborhoods? So the work that Chris and I did together was to give a kind of formal account of how that could be done, right? So we gave a method for defining generality precisely if you've given those two things, given a domain and a method of measuring that domain. So that's sort of the core of my thesis, really. This is the core formal apparatus that I use throughout pretty much the rest of the thesis to explain everything else that I want to say. So my focus is mainly on biology, and so I talk about a bunch of different domains of possibility within biology. So my favorite example is the protein universe. It's a set of all possible proteins. Proteins make up about 20% of your average person's body mass, and a protein is just like there's these little molecules called amino acids, and there's about 20 types of amino acids in life on Earth, and a protein is just like a long string of amino acids. It's a sequence of different amino acids, and then they spontaneously curl up into a 3D shape. So the space of possible proteins is usually talked about in terms of the space of possible amino acid sequences. Right? So all of the different ways that you could string together amino acids in a linear chain is the space of possible proteins. And biologists sort of argue about how much of that space life has realized. So, there's several million proteins that we've characterized in life on Earth. There's probably a lot more than that hanging around, but that's sort of tiny fraction of this actual space of possibilities, which is vast beyond comprehension. It's if you want to know that's the number of possible sequences, it's something like 20 amino acids raised to the power of however long the protein is. So if it's 200 amino acids long, you've got 20 to the power of 200 possible possible protein types, which is quite a few. So that's one domain of possibilities in which something could be general or non-general. I also talk about other domains like the domain of possible coiled shells. So this is something that biologists have been investigating as well. If you define a few simple variables over how a shell sort of like spirals out, it has a kind of like a generating curve that moves around, and you can characterize all the possible ways that a coiled shell could be, how fast the thing expands and how tight the curl is and so on. So, and they can actually fit a bunch of different species into that space of possibilities. So characterizing that kind of thing took up a whole bunch of my thesis, where I'm just looking at different domains of possibilities and how scientists define generality in those domains of possibilities, right? And using measure theory to make that precise. Having worked out this nice, precise language for talking about generality, I was finally in a position to go back to the original project that I started back in 2009 of characterizing emergence in terms of generality. So using this measure theoretic language to formulate the idea that I started in grad school with. And it goes, something like this. We'd say there's a micro level and a macro level. So there's a micro domain, so a space of possible ways in which the parts of a system could be arranged, and then a space of possible ways it could be arranged as an overall whole, right? So all of the different ways that your atoms could be arranged, or your microdomain, and all of the different ways that your sort of like overall organization could be is your macrodomain. Now, if it's the case that you can give a really nice p-general explanation of something at the microdomain, then it's not emergent, right? You should just accept that that's best explained in terms of the properties of its parts, right? You give this nice general explanation of how the parts are behaving. If, on the other hand, you can give a nice general macro explanation, so general p-general with respect to the macrodomain, but only a contingent explanation at the microdomain, then you should call that something that's more than the sum of its parts in explanatory terms. So that's the thing that cost me 8 years of my life to express. I hope you enjoyed that, but I should probably characterize it in somewhat more intuitive terms, because that's just sort of the technical philosopher's way of saying it. So maybe in non-philosopher talk, we can try one more time to explain this idea in more intuitive terms. So compare a living thing with a clock. So a clock is the classic example of a mechanism, right? It's something that's best explained in terms of the properties of its parts, right? So if you want to know why a clock does what clocks do, suppose it's a mechanical clock, what you can do is take the clock apart. right? And you can look at the stable properties of its parts. It's got a bunch of gears and springs, and those parts have a reasonably stable sort of properties like their rigidity, the number of gears they have, how springy the springs are. All of these properties are stable in the sense that if you take the clock apart, if you reduce the thing down to its parts, they've still got all of the properties that you would use to explain it as a whole, right? So the parts have their properties in this sort of regular, robust, general way, right? You could melt them down and remove those properties from them, but under the normal range of circumstances that we encounter, the parts have their properties in a very stable way, right? So they're stable general features which underwrite the explanation of the whole at the level of the parts. Okay, so that's a mechanism. It's something where the reductionist strategy works great. Right? That's a big success for the reductionist way of treating the world. Now compare that to a living thing, right? So if you take me apart into my parts, they very quickly lose the stability, like the properties that made them apt for generating me as a person, right? So if you take out my liver, it doesn't stay a liver for very long. It will very quickly turn into a pile of stinky mush, right? Like apart from the careful, delicate balancing act that my body is constantly performing to keep me alive, my parts very quickly will lose the properties that they need in order to fulfill their role in my organism as a whole. Right? So I have my parts, but their properties are not general properties of those parts. Right? They're not features that the parts will have regardless of what's going on. They're features that are actually highly contingent. Right? So they're arranged in these very specific ways, and they need to be held within very specific boundaries in order to have the properties that make them useful for keeping me alive. So if you want to explain something like me being alive, citing the properties of the parts isn't as good of an explanation as citing my overall organization as a whole, right? Because my overall organization as a whole keeps me regularly, I wake up every morning, so there's very regular generalization about me that I'm a living thing, but you won't be able to derive that I'm a living thing just by looking at the parts that I'm made of. You have to look at how they're organized and how they're integrated with each other. In philosophy, it's very unlikely that you're going to say anything that's completely original. Like the chances of that are very low, and in this case, that's absolutely true. There's a nice historical precedent for this kind of way of thinking about self-organization and mechanisms. So the very famous philosopher Immanuel Kant said something quite similar to what I'm proposing in my thesis. Hopefully I'm proposing more modern and fancy terms for talking about this, but I think the basic idea is the same. So Immanuel Kant says, look, you can't explain why organisms are the way they are mechanically. That is, you can't cite the general features of their parts to explain why they are the way they are. And that's because the parts are arranged, from the perspective of the parts, very contingently, right? So his example, birds have hollow bones, right? Why do birds have hollow bones? Well, there's no mechanical reason in terms of like that they could not have been otherwise. Lots of animals have solid bones, right? Big, heavy, solid bones. It's only when you consider the bird as a whole, like the fact that it needs to fly, and its flying is part of its way of getting around in the world. So it's only when you consider the bird's lifestyle and the whole ecosystem in which it's embedded and its way of living and all of that stuff that you can explain why it's got hollow bones. There's nothing about the bones themselves that will tell you. So if you want to use the reductionist strategy on a bird, take it apart into its parts and examine the parts, that's not going to tell you why they're hollow rather than solid. Furthermore, Kant points out that all of the parts of every living thing have this really, really specific arrangement. Like every single part is incredibly finely tuned to help every other part keep the whole thing going, right? So this is what he called self-organization, right? So you get this very, very specific arrangement of the parts that if you were just considering them as parts, maybe wouldn't make that much sense. But once you consider them as an integrated whole, suddenly they make tons of sense, right? So my parts are the way they are because they're trying to keep me alive, right? Well, they're trying to. They are the way they are because that's what does keep me alive. And you can imagine vast, huge spaces of other ways that my parts could be arranged. Like the exact same molecules, even the exact same organs, could be put together in a million different ways. But the fact is that they are the way they are because of the way I'm organized as a whole. And this is not just me, of course. This is all living things have these highly contingent, from the parts perspective, arrangements that make perfect sense if you consider them from this perspective of organisms as a whole. So that's Kant's thought, and I hope in my thesis I'm offering kind of a modernized version of this. So that's pretty much it. That's the gist of my thesis. If you want a quick moral of the story at the end here, I would suggest the following two things. First, that we can at least imagine how the manifest and scientific image of ourselves could both be true. So it's both true that you're just made up of atoms, but it's also true that you're a whole person, an agent in the world, an active part of everything. Like, you're part of the causal story of the world. And it doesn't have to be that your best explanation of you is just chemistry or just physics. The other thing that I would say is that if you find yourself threatened on all sides by the possibility of disillusion, death, and failure, then congratulations, you're a living thing and you're more than the sum of your parts. So don't take it too hard. If it looks like you're constantly under threat of falling apart, that's what it means to be more than the sum of your parts, is that your parts don't guarantee that you are who you are. It's you as a whole organism that does that. Okay, that's it. Thanks for watching. Quick thanks to everybody who helped me with this project. There's so many people, I can't possibly name them all, but especially Dennis Walsh, my advisor, my committee members, Philippe Huneman, Paul Thompson, the members of my final oral exam committee, Margie Morrison and Andrew Wayne, all of my friends at the IHPST who gave me excellent feedback, and over the years, especially Chris Belanger, who didn't just give me feedback, but actually was an essential part of this project, to Alex Koo, who let me use his great webcam setup and gave me sage advice as I came to the end of my PhD, and very especially to my friends and family who sort of kept body and soul together over the course of this project. I couldn't have done it without any of you. So, thank you.